Hi everyone, myself Siddharaju, Assistant Professor of Chemistry. In this session I am going to discuss about crystallography. It is for the BSc third semester. Here I am considering elements of symmetry in cubic crystals, law of rational indices, Weiss and Miller indices. Let me discuss about each of them in detail. The first one is elements of symmetry. To understand the concepts of elements of symmetry, it is needed to recall few things which we have studied in our previous classes. Have a look at this. It is a unit cell which is characterized by 6 parameters A, B and C. These are the edge lengths of a unit cell. Alpha, beta, gamma. These are the angle between the edges. And one more thing, crystals have an ordered internal arrangement of constituent particles. This ordered arrangement shows a symmetry. That means, in addition to the 6 parameters that characterizes the unit cell of a crystal, the crystal is associated with one more important property, that is what we call symmetry. Then what is meant by elements of symmetry? Elements of symmetry is a geometrical entity about which a symmetry operation is performed. Then what is symmetry operation? So to understand this, you just consider a picture. So it is a two-dimensional representation of constituent particles in a crystal. When I rotate this to an angle of 90 degree, it will give this structure. So this structure is similar to the previous one. So to understand the rotation, I have colored this lattice point. So on rotation to an angle of 90 degree, it will comes over here, but the appearance doesn't changes. When I rotate it again through an angle of 90 degree, this point comes over here, but the appearance will be same as the previous one. It goes on like this. So this rotation is called a symmetry operation. That means an operation that can be performed either physically or imaginatively, that results in no change in the appearance of an object, is called symmetry operation. So this rotation, what we call symmetry element or elements of symmetry. A symmetry element can be a point, axis or a plane. The three types of symmetry elements associated with a crystal. They are center of symmetry, plane of symmetry and axis of symmetry or line of symmetry. Let me consider these three kinds of elements of symmetry in detail. The first one, center of symmetry. It is indicated by the symbol small I. Center of symmetry can be better understood by considering this example. Here I have taken a circle, a square and a triangle. Circle and square are having center of symmetry, but the triangle is not having a center of symmetry. Then what is meant by a center of symmetry? It is an imaginary point within the crystal such that line passing through this point intersects the opposite faces of the crystal at equal distances. See, let me consider this point in a circle. When I draw a line passing through this point which intersects the opposite faces at an equal distance. See, you may consider it as vertically or horizontally. So we can find the same kind of imaginary point in the square also, but we cannot find it in the triangle. Hence, it is not having a center of symmetry. Next one, plane of symmetry. It is represented by the symbol sigma. It is defined as an imaginary plane passing through the crystal such that it divides the crystal into two parts in such a way that one part is the mirror image of the other. That means an imaginary plane which divides the crystal into two parts in such a way that which are mirror images to one another. Plane of symmetry of a cube is of two types. One is rectangular plane of symmetry. So you just consider this picture. Here we are having two vertical plane of symmetry, a rectangular plane of symmetry. Here this is one, a vertical rectangular plane of symmetry, and this is also a vertical plane of symmetry, and we can also find a horizontal rectangular plane of symmetry. That means a cubic system has three rectangular plane of symmetry. Another one, diagonal plane of symmetry, that is an imaginary plane which divides the unit cell diagonally. See, these are seems to be mirror images to one another. We can find 6 diagonal plane of symmetry in a cubic system. And one more element of symmetry, that is axis of symmetry, represented by a symbol Cn, an imaginary line passing through the center of the crystal such that if the crystal is rotated about this axis, it presents the same appearance more than once during the complete rotation through an angle of 360 degree. See, which can be understood by considering these examples. So here I have taken a unit cell of a crystal. This is the imaginary line about which we can rotate through an angle of 60 degree to get the same appearance. That means when we rotate this crystal to an angle of 360 degree, we will get the same appearance 6 times. Hence this line is called 6-fold axis, or it can be represented as C6 axis. Let me consider one more example. This is the imaginary line or axis about which we can rotate the crystal to an angle of 90 degree to get the same appearance. That means when we rotate the crystal to a 360 degree about this axis or a line, we will get the same appearance 4 times. Hence, this axis is called 4-fold axis. It can be represented as C4. Let me take one more. When I rotate this unit cell along this line, it will give a same appearance after rotating it to 120 degree. That means on complete rotation to a 360 degree, we will get the same appearance 3 times. Hence this line is called 3-fold axis of symmetry. And you may consider one more. So when I rotate this unit cell along this line, we will get the same appearance after rotating it to 180 degree. So we will get the same appearance 2 times when we rotate it to a 360 degree. Hence this line is called 2-fold axis, or it can be represented as C2. Now you consider elements of symmetry in cubic crystal. That means we have to calculate the number of elements of symmetry present in a cubic crystal. So you just try to understand this point. The crystals of a particular substance always possess the same elements of symmetry. This is what we call law of symmetry. A cubic crystal always possesses the following different elements of symmetry. So there you just consider. Here I am taking the possible elements of symmetry present in a cubic system or a cubic crystal. So let us count them. The first one indicated by A. This is a rectangular plane of symmetry. There are 3 rectangular planes of symmetry. And B, it is a diagonal plane of symmetry. I have discussed about this. There are 6 diagonal plane of symmetry in a cubic system. And this is the line. It is called a C4 axis, 4-fold axis of symmetry. We can find 3 4-fold axis of symmetry in a cubic system. So this is one is along this direction, another one is horizontally, and one more in this direction. So we can find 3 4-fold axis of symmetry. And D, this is 3-fold axis of symmetry. So we can find 4 3-fold axis of symmetry in a cubic system. And it is 2-fold axis of symmetry. We can find 6 two-fold axis of symmetry in a cubic system, and one more is the center of symmetry. So totally there are 23 elements of symmetry in a cubic lattice or cubic system. Now the most important point to be considered in crystallography is the law of rational indices. First, you try to understand the definition of law of rational indices. The intercepts made by any plane or face of the crystal on the crystallographic axis are either same as those of the unit plane or simple whole number multiplies of those of the unit plane, or one or two intercepts may be infinity. So that means these points to be considered very carefully. See, the intercepts made by any plane or face of the crystal on the crystallographic axis are either same as those of the unit plane or simple whole number multiplies, or it is infinity. Now let us try to analyze them. See, here I have taken a crystallographic axis. It is x axis, a y axis, and it is a z axis. Here I am considering a plane, a unit plane indicated by A, B, C. That means a plane cuts the x axis at the point A, which cuts the y axis at the point B, and which cuts the z axis at the point C. And A is the intercept along the x axis, B is the intercept along the y axis, and C is the intercept along the z axis. Now I am considering it is a unit plane. Hence the intercept along the x axis is a small a, along the y axis is a small b, along the z axis is a small c. Now you consider the coefficient of the intercept, that is 1, 1, 1. This is what we call Weiss indices. So let me take one more example here. I am considering a plane that is represented as KLM. So it cuts the x axis at the point L, it cuts the y axis at the point M, it cuts the z axis at the point K. Let the intercept of this plane along the x axis be a small l, along the y axis be a small m, along the z axis be a small k. So this intercept of this plane KLM plane is related to a intercept of a plane, unit plane ABC. That means this L, the intercept of this O to X, L will be a integral multiple of A. So where n is a integral multiple. Then again M, this intercept will be a integral multiple of this length B, small b, it is indicated n dash, and this intercept a small k will be a integral multiple of the intercept of a unit plane, that is C. So when you consider the intercepts of this plane KLM along the x axis, y axis and z axis, it will be n times of A, n dash times of B and n double dash times of C. So this n dash, n double dash is called Weiss indices. See here, the intercept either it is same as in the unit plane or it is an integral multiple of the intercept in a unit plane. Now let us discuss about the Weiss indices in detail. The coefficients of intercepts of a crystal plane on a crystallographic axis are called Weiss indices. So they can be calculated by using this relation. Weiss indices is equal to intercept on the axis divided by unit length on the same axis. So this can be better understood by considering an example. Here I have taken an unit cell. So I have considered a unit plane. See, the edge length will be a small a, it is a small b and it is a small c. Now you consider this. So if I consider the intercept along the x-axis, see, intercept on the axis, it will be a divided by unit length on the same axis, it is also a. As the plane touches this point, it will be a divided by a itself. So along the y-axis, intercept on this axis will be b as it is touching at this point. Unit length on the same axis will be a itself. Then along the z-axis, intercept on this axis will be c. Unit length on the same axis will also be c. So when you simplify it, it will be 1, 1, 1. This is the Weiss indices for this plane. Okay. Let me take one more example. Here I am considering this plane. So if you consider this cube, this is the face which is towards us. It cuts the x-axis but not the y and z-axis. So for this, you just try to write the Weiss indices. Along the x-axis, intercept on the axis, it is a as it is touching at this point. Unit length on the same axis is a itself. When you consider along the y-axis, this plane is not cut the y-axis anywhere. So it is parallel to the y-axis. Hence, intercept on the y-axis will be infinity times of b divided by unit length on the same axis is b itself. So along the z-axis, so this plane is not cut the z-axis, hence it is parallel to the z-axis. Hence, intercept on the axis will be infinity times of c divided by unit length on the same axis is c. So when you simplify it, it will be 1, infinity, infinity. That means this intercept will be infinity only when the plane is parallel to any axis. Then one more important thing to be considered, Miller indices. The reciprocal of coefficient of intercepts of a crystal plane on a crystallographic axis are called Miller indices. Miller indices are always a whole number. They can be represented by the symbol HKL within the parenthesis. There should not be any comma between them. Now, you try to understand how to write the Miller indices for a particular plane in a crystal. See, here I have considered an example. Here I have taken a plane which cuts the x-axis at this point, which cuts the y-axis at these points, but it doesn't meet the z-axis. It is parallel to the z-axis. The steps involved in writing the Miller indices are, first you try to write the intercepts. So I have taken A, B, C, it is along x-axis, y-axis and z-axis. This is the edge length. Intercepts you consider, as it cuts the x-axis at the point itself, it will be a divided by a, it is 1 only. As it cuts the y-axis at this point, it will be b divided by b, it is 1 only. But it is not cut the z-axis, hence it is infinity. Then after writing the intercept, you take the reciprocal of it. So 1 divided by 1 I have written, it will be 1 itself. B, it is 1 divided by 1, it is again 1. It is infinity, 1 divided by infinity is 0. So if we get any fractions here, we have to reduce it to a whole number. So here there is no problem, they are all whole numbers 1, 1, 0. Hence the Miller indices is 1, 1, 0 for this plane. Let me take another example. Here I have considered a plane which cuts the x-axis here, but it is not cutting a y and z axis. See, first you try to write the intercept. See, it is off of the mark. So edge length is a, it is cutting the x-axis at the middle of this. So intercept is 1 by 2. So along the y-axis, it is infinity because it is parallel to y-axis. So for the z-axis, it is infinity, it is parallel to the z-axis. Then you take the reciprocal of it. 1 over half, it is 2, 1 divided by infinity, it is 0, 1 divided by infinity, it is again a 0. So then you reduce it, there is no fractions are involved here, so it is 2, 0, 0 itself. So the Miller indices are 2, 0, 0 for this plane. Let me consider one more example. Here I have taken a plane which cuts the x-axis here, which cuts the z-axis here, which cuts the y-axis here. So first you write the intercepts. So A, it will be off, the point is in between, or it is a middle point of this edge length. B, it is 1 as the plane meets at this point itself. Then intercept along the z-axis is 3 divided by 4, 3/4 of the edge length. Then you take the reciprocal of the intercepts, it is 1 divided by half, it will be a 2, 1 divided by 1, it is 1 itself, 1 over 3 divided by 4 is 4 by 3. See here we have a fraction, we have to convert into a whole number. So you just multiply all the 3 values by 3, we will get a 6, 3 and 4. So the Miller indices for this plane will be 6, 3, 4. So these are the important things to be considered in this session. So far I have discussed about the elements of symmetry, then the types of elements of symmetry, law of rational indices, Weiss indices and Miller indices. Hope you understood them. Thank you very much.